across the country, making it this a truly exciting and inspiring gathering. As a part of the meeting, today's public event, Charting India's Cosmic Odyssey, from Earth to the Edge of the Universe, is our opportunity to share the wonders and progress of cosmology with the general public. Cosmologists often describe the universe's history in three broad epochs: the early, intermediate, and the late universe. And today's talks are guided through that grand timeline. We'll explore the origin and evolution of the universe, from theoretical insights to observational triumphs, with a focus on India's growing role in cosmology and space science through major experiments and missions. Now let me introduce you to our speakers for this evening. Professor L. Sriram Kumar from IIT Madras, Chennai, will open the session with his talk, Mapping the Cosmos, General Relativity and the Timeline of the Universe. Professor Tarun Sorodip, who is the director of the Raman Research Institute, Bengaluru, will delve into the early universe with his presentation, Echoes from the Beginning, Echo from CMB Bharat. For the intermediate universe, Professor Tirthankar Roy Choudhury from the National Center for Radio Astrophysics, TIFR, Pune, will present From Darkness to Light, the SK's quest through cosmic time. And finally, exploring the late universe, Professor K.G. Arun from Chennai Mathematical Institute will talk about gravitational waves in his presentation, Ripples in Space-Time, LIGO and the Late Universe. The event will be moderated by Professor Susmita Adhikari from IISER Pune and Professor Ranjan Laha from IISc Bengaluru, who are also co-organizers of this national meeting alongside the three speakers of this session. To formally open the event, I now invite Professor V. Ravindran, Director of IMSC and a renowned physicist in the field of quantum chromodynamics, to say a few words. Following that, Professor Adhikari and Professor Laha will take over and guide us through the evening. Thank you, and we hope you enjoy this journey through the cosmos.
Dheeraj? No, thank you. Sorry. Okay, so warm welcome to every one of you here. It's indeed a great pleasure to welcoming you. The meeting started a few days back, but I was unfortunately with other meeting, so I could not actually formally welcome all of you. So I take this opportunity to welcome those who have come for this meeting. That's my first welcome. The second welcome to those who have come for this, this special event. It's outreach event, which is part of this, this big program. Those who have just come for that, actually, I want to sort of welcome those people as well. And for those who are the first timers in this institute, I want to sort of give a brief introduction to our institute. Okay, maybe you all know, but it's customary to do this. We have 4 groups in our institute: theoretical physics, mathematics, computation, theoretical computer science, and computational biology. As you can see, the variety of things that we do. In fact, it's just broadly it's 4. If you really look at individual faculty, every faculty works on completely unique areas in science, actually, as you can see. So we have, I can proudly say that we have 50 different departments. Okay, there are 50 faculty members working on really 50 different things. So it's an unique character of IMSC, and we have several programs to sort of showcase things, invite people, have various programs of this kind. This is one of them, and it's a unique event, actually. Unique in the sense because this is an event which Dheeraj has actually initiated. This is the annual event, and we can call it the first edition of that annual event that we will have every year. And this event is a very special because, as I heard from one of the speakers of today, almost 99% of cosmologists from India are here, actually. So this is a kind of a galaxy of cosmologists. So I'm really happy that all of you could make it to our institute to participate in the meeting that Dheeraj is organizing. So I want to congratulate him for bringing all of you here. Okay, so that's first thing I wanted to sort of say. And IMSC is known for outreach activities that many of the people who are associated with IMSC would agree with me, because we regularly have outreach activities for starting from school kids, college students, and even teachers of the school and college lecturers of the college, and at various levels. Actually, many of our faculty members are involved in outreaching, because outreach is very important component of any research institute. Otherwise we won't get, that's the catchment area we call actually. So along this line, I think Dheeraj has very intelligently thought about this component to include in this meeting, and he has successfully included this nice component of this meeting, which is outreach. And we have four the most renowned people in cosmology. He named all of them actually. We all know them actually, either through their talks or through their names or work. And today you're going to hear talks by them. I think it's really, I'm really thankful to all these four speakers who have really agreed to speak in the language that people like me also can understand. So that's an important aspect of this meeting, that we have this outreach activity. And I wish this program continues, both this annual event along with this outreach event, so that it reaches to people who are not familiar with this subject. Actually, it's a very important thing that we should have. So I won't take much of your time, and I leave this floor to the speakers, and you'll have a wonderful time. And of course, he has some very special dinner arranged for us actually. So with that, I'll again welcome all of you. Have a wonderful evening and the rest of the meeting as well actually. Thanks.
Okay, so welcome everyone to this public event. So as Dheeraj said, we'll be hosting it. So the first, we'll start first from a theorist, and then we'll go to early universe cosmology, so-called the Middle Ages, and then the late universe cosmology. So the first talk will be given by Professor L. Sriram Kumar. Professor Sriram Kumar did his PhD from IUCAA, then he did his first postdoc at Hebrew University in Israel, and then Alberta University in Canada, and then he was a faculty member at HRI, Harishchandra Research Institute in Allahabad for about 10 years, when he moved, and then he moved to IIT Madras in 2011. Professor Sriram Kumar works on a lot of topics in theoretical physics, cosmology, inflation, dark matter, primordial black holes, and also many theoretical calculations which are required for inflation. And today he will be talking to us about mapping the cosmos, generativity, and timeline of the universe. So the talk duration is for 20 minutes each. And after each talk, we'll take a few questions from the audience, preferably from people who are not attending the scientific component of the meeting. Others are also welcome to ask questions, and then we will go like this. Okay, thank you. Thank you, Professor.
Thank you. Thank you, Ranjan, for the introduction. I should begin, of course, by thanking Dheeraj and IMSC both for hosting this meeting and also giving me an opportunity to speak at this meeting. Humankind has always looked at the night sky with awe and have wondered how the stars have all come about. Over the last century or so, we have made tremendous progress in the scientific understanding of our universe. In particular, over the last 20 years, giant strides have been taken in the field of observational astronomy, which has led to some amazing discoveries and fascinating conclusions. Our current view of the universe is often referred to as the standard model of cosmology, or popularly as the hot Big Bang model. According to this model, the universe began with a bang. It was hot, it cooled down as it expanded, and there were tiny inhomogeneities that were present in the early universe, which grew over time due to gravitational instability to form the structures that we see around us as galaxies and clusters of galaxies. In this talk, which I have planned for a non-specialist audience, I will try to outline the observational evidence and the theoretical underpinnings that go into the Standard Model. Here is an outline of my talk. Before we try to understand, construct a theory of the universe, we need to know what the universe contains. And we will see that the universe is not static, though it seemingly looks so, and it is in fact expanding. And if you're a school student, you would have heard about the Newtonian theory of gravitation. On these large scales, the Newtonian theory is not valid. You need to turn to a more modern theory called general relativity, which helps us understand the expansion of the universe and its consequences. And we will see that the universe not only contains matter, it contains radiation. When one says radiation, you will think about starlight essentially, but we will see it is a different type of radiation that pervades the universe, which we'll call as the cosmic microwave background. And then we will talk about, I mentioned about the perturbations present in the early universe. We will see the standard hot Big Bang model is not able to explain the origin of these perturbations. You need to add another paradigm, attach another paradigm to the hot Big Bang model in order to explain those perturbations, which are remarkably consistent with the data, as I will explain, and my speakers who follow will explain as well. And then I will talk about the generation and evolution of these perturbations, how they go on to form these structures in the universe that we see. What does the universe contain? Oops, what happened? Okay, something is loose connection. No, I have to mirror that.
Yeah, I think so.
But I have done that. Anilama. Keep the changes. Okay. I'm hoping, no, it's not showing up. மிரர்ல தான் இருக்குல்ல, ஏன் வர மாட்டேங்குது? ஓ, வந்துடுது.
ஃபுல் ஸ்க்ரீன் பண்ணாது வர மாட்டேங்குது. ப்ராப்ளம் மேபி சீட் எப்படி?
Yes, sorry about that. Please bear with us. இதுல பண்ணலாம். Yeah, I'm trying to. Okay.
This is coming.
Yes.
It's not coming, it was coming. This. Yes, maybe make it bigger. This slide. This should be full screen. Yeah.
Okay.
Yes.
I'll just leave it there.
Like that.
Yeah. All right. Sorry about that. Well, remember, we are interested in understanding the universe as a whole. We are not interested in local astrophysical objects. And one of the simplest units in our universe is our galaxy. And our own galaxy, as you may know, is referred to as the Milky Way. If you wish to know the dimensions, it's about 15 kiloparsec. A parsec is an accidental unit of about 3.26 light years. And there are many, many galaxies around us. One of the largest nearby galaxies is called the Andromeda Galaxy. It's located at a distance of about 700 kiloparsec, and its many ways is similar to our galaxy. But much like, clusters of planets, as the solar system, or clusters of stars that we see within our galaxies. Galaxies themselves cluster, and they form what is known as a local group of galaxies. About 30 of them form a local group which extending over about a megaparsec or so. And when you look beyond, we are part of what is known as a Virgo cluster of galaxies. Each cluster can contain about 10 power 2 to 10 power 3 galaxies. We are at the edge of a Virgo cluster heading towards its center. And there are other such clusters. Each extended object in these images is a galaxy in itself. This is a Coma cluster, and there is a Hercules cluster, and so on. And one of the deepest views in space was due to HST earlier. Each extended object again is a galaxy, and you can see a more modern image taken by the James Webb Space Telescope on the right. But we would like to understand what the universe contains as a whole, and one of the largest such surveys is due to the SDSS survey, and I will just play a movie that the SDSS team created. Okay. And what it does is that we start from our galaxy and we go away from our galaxy, and the speed of this movie doesn't play any role in our discussion, and you will see two yellow spheres that appear, one at a distance of about 1 million light years and another at a distance of about 1 billion light years, which will come eventually. There is hardly any galaxy between us. Remember, the closest large galaxy is Andromeda, which will quickly appear from the left, which is at a distance of about 2 million light years. And as you go further, you will see there will be more and more galaxies that will come into our view, and you will see, though the universe is rather clumpy on small scales, I will I will indicate what that scale is. This is the Andromeda galaxy I mentioned, which is at a distance of about 2 million light years, and on larger and larger scales, in fact scales of about 80 to 100 megaparsec, what you find is that there is a fairly uniform distribution of galaxies in the universe. And it's often referred to as the universe is homogeneous and isotropic on large scales. What it means is that if you take a sphere of a radius of about 80, 100 megaparsec and you place it at different locations in the universe, you find that they will contain roughly the same amount of matter, independent of where you place and which direction you place. And what essentially I'm saying is that if you take one of these slices and average over about a scale of about 100 megaparsec, and independent of where you place and which direction you place, you find the universe to be, the spheres to contain the same amount of matter. On large scales, the universe is homogeneous and isotropic. This will play an important role in trying to understand our universe. And I will just stop here for want of time and proceed with my slides. So we have these galaxies on the larger scales, but then we find that the universe is also expanding. How do we arrive at this conclusion? Well, we have different spectra of different galaxies here, and they will have telltale emission and absorption lines, and there will be astronomers who can, looking at the spectra, immediately identify what type of transitions they correspond to. And now, if these are spectra from different stars, some of the close by spiral galaxies, and now if you look at galaxies at different distances, what you find is that you take a standard line, which is called the H alpha line, which is located somewhere here, and you see that they all get shifted towards the longer wavelengths or the red end of the spectrum. And the farther away a galaxy is, one finds that the shift in the spectral lines, it's not just a single spectral line, the entire spectrum is stretched towards the red end of the spectrum. And this is often referred to as redshift of galaxies. And what does it imply? Essentially, if you turn to the Doppler effect, you will conclude that they are moving away from us, and we will see very quickly that is not the manner in which you need to interpret the cause of this redshift. If you try to plot, if you attribute a velocity as you would due to the Doppler effect and plot it as a function of distance, strangely what you find is that, or interestingly, what you find is that they have a linear relationship, and the slope plays a crucial role in cosmology today. It is something that is still to be determined very precisely. And this is the original Hubble plot, which is about 100 years old. And there the slope was determined to be this, about 500 kilometer per second per megaparsec. What it implies is that two galaxies that are separated by a distance of about a megaparsec are moving away from each other with a velocity of about 500 kilometer per second. A more modern Hubble diagram is this one. This red square indicates the older Hubble diagram. Evidently, we have been able to measure this to larger and larger distances, and the distance is somewhat non-trivial to determine, and that is the reason for the uncertainty in this value. And the slope of this curve is often referred to as the Hubble constant, and you may hear about something related to the Hubble tension. And if you know, the more modern value is close to about 72 kilometer per second per megaparsec. The picture that this yields, is as follows. You have galaxies which are moving away from each other. Imagine a situation where you run this movie backward. You have a situation where it seems that the galaxies were on top of each other and eventually moving away at an earlier time. And there was this explosion, which is, referred to as the Big Bang. And due to this explosion, so to say, that these galaxies have been thrown apart, and it is moving with various velocities depending on the distance from us. This is not the correct picture. As I mentioned already, the Newtonian theory of gravity is not adequate to describe our universe. You need to turn to a relativistic theory, and one of the simplest relativistic theory to describe gravity is general relativity, which was formulated by Einstein in 1950. What it essentially tells you is that, as a famous quote originally due to Wheeler, it says, space-time tells matter how to move, and matter tells space-time how to curve. Think of the one simple way to think of it is think of a rubber sheet, and the moment you place a heavy ball on it, now if you drop a marble in this rubber sheet, it will move along the lines, along the bell, so to say, created by the bigger ball. And this bigger ball, essentially you say, has curved the space-time. It's no more flat. The rubber sheet is no more flat. And the marble follows according to the curvature, so to say, of the space-time. And using this general relativity, what you can show is that, these redshifts that I talked about of these different galaxies arises due to the expansion of the universe. You should not be thinking of these galaxies as though they are running away from us in some embedded space, embedded in a space. The space-time itself is expanding. And one simple way of thinking this is, put dots on a rubber balloon and inflate this balloon, and what you will find is that as you inflate this balloon, let these yellow dots be the galaxies, and as you inflate this balloon, the distances between the dots on the balloon increases with time. And this is a nice simple way of visualizing an expanding universe, and using general relativity you can show that it is the expansion of the universe that causes the redshift, as this artist has tried to indicate in this picture, in this cartoon. So we have an expanding universe. There is evidently matter present in the universe. What else is present in the universe? Evidently, there is light, stellar light present in the universe. What you can do is that you can, just like we took a stock of all the galaxies around in our universe, you can take stock of radiation in the universe, and what you arrive at is an image, is a figure like on the left. You have the intensity of the radiation plotted as a function of wavelength, and what you find is that, there is a peak somewhere in the microwave region of the electromagnetic spectrum, and the rest of the entire, radiation from stars and other sources do not compare to the amount of energy in radiation in this microwave region of the electromagnetic spectrum. And if you zoom in into this part of the spectrum, what you find is it's a nearly perfect thermal radiation. It's a perfect black body radiation at a temperature of about 2.725 Kelvin. Now, with general relativity and this conclusion that you have a perfect thermal black body radiation, you can immediately show as the universe expands, the temperature of the radiation roughly falls as the manner in which the universe expands, or the size of the universe, so to say. Or in other words, as you run this movie backward at an earlier time, what you find is that the temperature of the radiation will go higher as the universe at the early times in the universe. So you have matter, you have radiation. The matter density falls as 1 over L cubed. Usually it's denoted as A cubed, A being the scale factor. Remember, I told you the distances between two different galaxies changes with time. You can characterize by the function A of t, say, and this is often referred to as the scale factor. Matter density, you know, goes as 1 over volume, therefore the matter density will go as 1 over A cubed. The radiation density, remember your Stefan Boltzmann's law, is proportional to T power 4. You can show that T, the temperature of this thermal radiation, is inversely proportional to the scale factor, therefore the energy density of radiation goes as 1 over A power 4. Or at an earlier time, the energy density of radiation is much higher than that of matter. In fact, you know, this leads to this notion of the hot Big Bang model, and this, I'm sure you know, it's from a popular sitcom, The Big Bang Theory, and the title song says, our universe starts in a hot, dense state, it expands as it cools down, okay, and, you know, as we will see, as it cools down, structures form. So what is the picture we have? We have a hot, dense universe at the early times. This yellow part, yellow fluid represents radiation. These red balls correspond to essentially protons in the early universe. The small red balls are electrons, and the large red balls are neutrons. So essentially, this is a hydrogen nucleus. This is an electron. At very early times, when the temperature was very high, what you find is that there was too much energy in the photons, and they wouldn't allow the electron to recombine with the with the proton. But as the universe expands, it cools down, and there comes a time when the photons are not able to knock off the electrons, and these atoms form. This is a hydrogen atom, and that's a cloud of electron around the nucleus, and this evidently is a helium nucleus, and there is a cloud of electrons around it. And so essentially what happens is that when this atoms form, so to say, decoupling occurs. Radiation stops interacting with matter, and these photons stream freely towards us, which is what we observe as the cosmic microwave background. So think of a photon in a cloud here. So it has a very small mean free path. It is colliding often with the water vapor, molecules of water vapor. But when it comes to the edge of the cloud, the photon starts streaming freely and reaches us, and that is how you observe the cloud. In much the same manner, the photon has a very small mean free path at early times, but there comes a time when this decoupling occurs and the photon starts streaming freely and reaches us, and which is what we observe as the cosmic microwave background. So what do you have? You have a sphere around us, which is often referred to as the last scattering surface, and this surface you can, and you have temperature on this surface, and you can represent this surface much in the same manner like, you have the projection, the so-called height of projection of the Earth, and imagine Earth and the temperature on the different locations of the Earth, displayed in this manner. You can display the temperature on this last scattering surface in the same manner. And what you see is that, as we will see, you have a 2.725 degree Kelvin temperature, more or less everywhere in the every direction of the sky, but there are tiny anisotropies. In other words, at the 5th decimal place, there are small deviations from this, mean value of the temperature, and we will try to understand why, what they can do. I really have run out of time, but I saw that Tarun has slides on the inflationary scenario, so I will just skip this part, and I will just move on. What essentially happens is as follows. You have, fluctuations generated in the early universe. I'm sorry about that. You have fluctuations generated during the early universe due to quantum fluctuations, and essentially it's much like still water being disturbed by a pack of stones, and what essentially happens is that they end up forming what we refer to as the anisotropies in the CMB. And thereafter, what essentially happens is that this is what we have observed, the Kobe as observed as the CMB. Tarun will talk about in further detail. Let me go back to my slides. And what thereafter happens is that these are the observations of these anisotropies. I've already indicated what this oval represents. It represents different directions on the large scattering surface. These correspond to temperatures which differ from the mean value of the order of about 10 power minus 5 Kelvin or so, delta T by T of the order of 10 power minus 5 Kelvin. They have been measured with greater and greater precision, originally by a mission called WMAP and later by Planck. And Tarun again will talk about what the Indian efforts in these directions will be. And what they essentially do is as follows. I need to make this full screen in order to make it work. So think of a situation. Okay. Yeah, it's not, okay, I don't think that is stopping it. No, whenever I make it full screen, but, okay, I have to change the slide. So think of a situation, it has gone all the way ahead. This is very early in time. You have smooth distribution of matter. Remember, I talked about how the universe was homogeneous and isotropic on large scales. The fact that the anisotropies in the CMB, that is the deviation from this 2.725 Kelvin, are small, indicate that the energy density in radiation was also small at early times. But there is an epoch of inflation which introduces tiny disturbances in this homogeneous distribution. The moment you introduce that and you reach this epoch, later epoch, when matter was dominated, matter begins to dominate, what you essentially have is structures form. Many such pictures have been shown in this meeting, computed, arrived at through complicated computer codes. And what you essentially see eventually at a redshift of 0 or today is a collection of structures, which we refer to as galaxies and clusters of galaxies. With that, let me just quickly summarize, okay? And before that, I will give you a quick outline of what I have talked about. So the universe, you can determine to be about 13.7 billion years. And as I mentioned, there was a big bang. There was a brief period of inflation, which I couldn't talk about, but Tarun, I presume, will talk about. And then those tiny perturbations generated during inflation, it is driven by scalar fields which have quantum component, and these quantum perturbations, quantum fluctuations, leave their imprints as anisotropies in the CMB. Then there comes a period where there are no structures in the universe. There will be a dark ages, which Tirth will talk about, and then the galaxies form. This is the period of cosmic dawn, when the first stars form, and then there is a various epoch during the matter domination. Again, Tirth will touch some aspects of it, and something which maybe Arun will talk about towards the end is what observations indicate is that we are going through a period of accelerated expansion driven by a strange source called dark energy. So in summary, according to the currently prevalent view, an inflationary epoch, which I could not speak about, introduces tiny fluctuations, it magnifies them, and they are at the, and converts them into what are known as classical perturbations. I showed you a distribution of particles with small deviations from smoothness. I'll wind up in 30 seconds. And then these inhomogeneities leave us imprints as anisotropies in the cosmic microwave background. It is these anisotropies which are amplified due to gravitational instability, and it converts these anisotropies into the large-scale structure that we see around us today as galaxies and clusters of galaxies. And increasingly precise observations of the anisotropies in the CMB and the distribution of the large-scale structure will allow us to construct the physics of the whole universe. And I'll just leave this, this slide with some information about ongoing and future missions. Thank you very much.
Thank you, Professor Sriram Kumar, for the wonderful talk. So are there questions, maybe preferably from people who are attending this event? Come on, don't be shy, you should probably. Right? Who? Yeah, you can.
I can't see any questions there. I think
Maybe people who are attending this meeting, if they have any questions. Professor Sriram Kumar. Shantanu.
So which mission, among this, which is your favorite mission? Or which are most excited about? I mean, there are lots of missions.
so. For me, as an inflationary theorist, I mean, the detection of the B mode is it'll tell me the scale of inflation if we can get to see that. If we don't get to see that, we'll have severe challenge understanding when inflation took place, what are the other consequences. Maybe gravitational waves that Arun may talk about may help us, but if we can see the B mode at R of 10 power minus 3 or something, I'm sorry to be getting technical, that will be exciting.
Okay. Thank you, Professor Sriram Kumar, for the answer. Are there other questions from the audience? Okay, if there are no more questions, let's first thank Professor Sriram Kumar for the wonderful talk. And for the next speaker, I'll hand it over to Professor Odhikar.
All right. So thanks Sriram for giving us a quick 20-minute recap of the last 13 billion years. So next we'll move on to Professor Tarun Shoradeep. So we're very happy to have him here. Professor Tarun Shoradeep is currently the director of RRI. He began his scientific career as an undergrad at IIT Kanpur, after which he did his PhD in IUCAA, which is in Pune. Then he moved on for his postdoctoral studies to the Canadian Institute of Theoretical Astrophysics, after which he came back to India at IUCAA, spent several years there, and then moved in about the last 10ish years, I guess, or 8ish years, he moved to IISER Pune, where he was the chair of physics, and then in the last 3 years, he has been at RRI in his current role. He has played leading roles in observational efforts in India for LIGO as well as CMB Bharat. His work has extensively covered the cosmic microwave background that we've been hearing about, the perturbations in the cosmic microwave background, inflationary physics, and large-scale structure. And today he'll be telling us about India's efforts to measure the CMB. So take it away. Sorry.
Thank you, Shushmita. Am I audible? Okay. So let me begin by thanking the organizers, but that's kind of for the invitation to Chennai Mathematical Institute, Institute of Mathematical Sciences, sorry. And also in particular, I should take this opportunity to thank Professor Ravindran for, giving this opportunity to the Indian cosmology community and, helping Dheeraj, encouraging him to have these regular meetings. And it's a great time for Indian cosmology to come together. A remark that I made, when I came in 2000, I think the front row would house the entire cosmology community of India, and now I'm really delighted that we have a very strong cosmology community in India, and going forward I think things will get better. Okay, so let me quickly tell you about some exciting possibilities that are opening up, and one is the echoes of the beginning. So this often I call the kind of looking for the origins of the universe, and that is something that is a scientific milestone that is just awaiting humanity. And you should just listen to the Nobel lectures of Kip Thorne and Ray Weiss, and you will find that they say the next milestone, and when they were being getting the award for the gravitational wave detection. They said the next big milestone is the primordial gravitational waves from the beginning of the universe. Okay, so that's the echo of the beginning, and we want to really see Indian community greatly involved in that in the coming years. Okay, so let me set the stage a bit for cosmology. You know, this is already done by Sriram. So if you look up, you know, you see the Milky Way. If you look away, you see the large scale structure. So the universe is full of galaxies, and if you put a distribution of matter uniformly in the universe, then general relativity, as Sriram told you, predicts an expanding universe. Now, I just wanted to point to one particular you know, implication of that. Essentially, I should also tell, if, I mean, I don't have undergraduates in here, but you know, typically physics for the cosmology, cosmology is fairly simple. It's regular physics done in this expanding background. There's nothing new, all the effects come out of the expansion. Okay, and one of the effects is what Sriram told you in words, and I'll tell you in pictures. So if you have a box in the imaginary box in the universe, and you look how many galaxies would be there in that box, the number will remain the same, box is becoming smaller. So the density of matter grows as cube of the size of the universe, and but radiation actually scales by another factor of distance, because the wavelength also shrinks when you go back in time. So the biggest you know, surprise here is the early universe is just radiation dominated. You may have whatever structures in the universe at present, but the early universe is very simple. It's a radiation soup, right? If you have any remnant of the radiation now, that will dominate the energy density of the universe in the past, and that's the simplicity that our, you know, model of the universe has. And if you do that, you know, you see that the universe going back would be hotter. If you look at a black body, you know, at higher and higher energies, it's got higher and higher temperature. So where was all this radiation? If the universe is radiation dominated in the past, is there any signature of that radiation? And that was serendipitously discovered by Penzias and Wilson when they were building the early radio antenna in 1965, and couldn't get rid of a noise which seemed to come at all times from all directions, and turned out that that was the cosmic microwave background. This is the remnant radiation of the universe, and Sriram showed you a plot to tell you that 99% of the energy in radiation is contained in this you know, isotropic and black body distribution at a temperature of 3 Kelvin. It may be surprising, but you know, gamma ray background, X-ray backgrounds don't even come close. The closest is an infrared background. And this is the clinching support for the hot Big Bang that you talked about. So again, since I'll be talking more from the observation point of view, from the observation point of view, this is again an amazing thing of nature, that when for any observer in the universe, if you peer further away, you are looking back in time. You know, if you look at the sun, you are looking at it as it was 8 minutes back. We may not think about it that way, but if you are looking at a distant galaxy, it could be millions or billions of years in the past. So if we, the question is how far back can we look in, how far out can we look in electromagnetic radiation? So it turns out in this band of say some tens of gigahertz to 1000 gigahertz, you can look almost all the way to 43 billion light years. Okay, that means you are looking at a universe which is way back in the early times, and so much so that as I said, the universe is hotter in the past. So the universe which is 3 Kelvin now, the cosmic microwave background you see is that 3 Kelvin will be about 3300 Kelvin, and that's enough to keep all the hydrogen and helium, which is the dominant matter, atomic matter content of the universe, completely ionized. So you have a completely ionized plasma surrounding you in this. So I call this the cosmic super IMAX theater. I mean, it's amazing that nature has given us this way to see the universe on the largest scales and up to a very, very early time. The universe was only 500,000 years old then. The universe is now about 14 billion years. Okay, so this is an amazing gift from nature. What have we done with it? So from 65 to 92, this looked like a glowing plasma screen, but it looked like there was nothing to read off it. It was just blank. It's all glowing at 3 Kelvin, but then they really improved the contrast to 1 part in 10 to the 5, 10 parts per million, and you started seeing things, and this is basically Kobe's Nobel Prize reason, right? And what did that tell you? That told you two things. One is there must be something which has perturbed the plasma in the past to have created those ripples. And secondly, if these ripples are there in radiation, these are good enough to grow by gravitational instability, because as even in Newton's theory, you know that if you have a uniform distribution of matter and you create a little inhomogeneity, that inhomogeneity is going to grow. It's an exponential growth, and it's a power law in expanding universe. So you can explain the existence of this large scale structure that Sriram showed from the SDSS and all, just based on this picture that you get at an early universe. So you are seeing the seeds of the perturbations which gave rise to the entire large scale structure of the universe. So that's the story that has played out in cosmology till now. Okay, from 1992 when Kobe results came out to now, we have been able to take this early universe picture, map it, match it with various understanding of our universe, and we have some understanding that 6 parameter model called lambda CDM seems to explain things to a large extent, but as you would have in this conference there were a lot of people talking about kind of trying to fix the niggles. So that's one part of the game that is of course should go on. The other part which is very important is we still have to explain all the deductions of our cosmology has been based on this belief that there is something that perturbed the early plasma, and that process has to happen very early in the universe. And this is some kind of, I'll just think of it like a tub, when you're putting it, you're just drumming it out here. Okay. So, okay, the question that, I put this slide because Sriram couldn't cover it. What Sriram was trying to get to is this sphere that I showed you, this plasma screen that you're seeing, two-dimensional universe will be this circle surrounding the observer, right? And what turns out in cosmology without inflation is that there is no way to causally explain why the temperature of the cosmic microwave background here and here are the same, because the past light cones of these two don't intersect. But if you have inflation, you can allow for a phase where this light cone can grow and overlap, and that is the reason inflation should be there. So this was the thing that we are looking for in the data. So now let me talk about what happened in the data. So this is again the sky converted to a globe picture. So in 1990s, as when I just started my PhD, Kobe discovered the first hints that the temperature was not uniform. There were small fluctuations at tenths of 30 microkelvin kind of a level on this 3 Kelvin background. Okay, that was refined in the next decade by Wilkinson Microwave Anisotropy Probe, which is shown here. That's a NASA satellite. This is also a NASA satellite. And then in the following decade, Planck absolutely, read off all the information that was there in the intensity fluctuations. All the information that is important for the kind of cosmology we are talking of has been entirely mined by Planck, And I should also mention, although there are 3 spacecrafts I am talking about, there were multiple experiments from the ground and balloon that did very interesting work. In fact, the first polarization was directed by, I think, where's this, Daisy, and going on, there are experiments going on now. Now let me try to tell you why we are looking at India trying to play a big role in the next CMB mission. We have had 3 major missions here and it's been very successful, right? The reason is a space mission is very important for the kind of science we are trying to do. That's because, you know, our atmosphere is transparent only in the band of radiation that we use for visual. So, there you can see everything comes through, but where we are trying to look, there are only small bands which are accessible from high altitudes on very dry places from the earth, right. And you can send up balloons to go above these altitudes, but then, you know, that's quite limiting. But in space you get access to all the frequency bands, you have access to the full sky, you do not have to contend with atmospheric changes. You know, space provides a very nice thermal environment for the detectors, and of course, if you go to the right place like a second Lagrange point, there is no radio frequency interference. But what did these three generations of you know, science do, I mean observations do? You know, we now have this 6-parameter model where, you know, things are known to percent level. The parameters of the model are known to percent level. This is unprecedented cosmology. I think Ravindran probably will realize that when we were students, no one thought cosmology would become a quantitative science like this. Things were talked about in factors of 2, right, a Hubble parameter in particular. So, we have now a model to stand on. I am not saying this is the final model, okay, but we have a model where we can quantitatively go forward. And I just want to illustrate why this is a big deal. So, from the day of COBE to now, our information that we have of the universe has increased by 1 billion-fold. This is just the inverse of the, you know, error covariance matrix in the multiple dimensions, at least by 1 billion times, or, you know, even 10 or 15 times for the simplest model. So, it's a phenomenal thing. It's 3 times the Moore's law. It's an extremely successful field of study, okay. So much so, I think the immense success of this field has sort of, you know, told people, oh, they must have finished everything. But at this point we are yet to go forward, and if we build a next generation satellite, we would improve this by another factor of 1 billion, right, the next generation that I will talk about, okay. And we have reasons to really probe our thing, because this is not the final model. You know, Jim Peebles, who is attributed to giving the, you know, CDM and lambda CDM ideas, himself at this post Nobel thing, you know, it's just startling that it has worked so well, but it's certainly not the final thing. Now, what is the big issue? The big issue is we have excellent observations, and we have pinned down a particular simple model of cosmology, but that model is not, you know, it is very exotic. We do not know 95% of the matter. It's cold dark matter, it is you know, dark energy or cosmological constant. All these are big puzzles in cosmology. So, a lot of the talks here focus on this, a lot of cosmologists worry about it. To me, the pressing point is, oh, what about those perturbations? You derived all these numbers assuming that there was a fluctuation spectrum. We do not have any clue as to what was the physics behind it. So, we should make attempts to go and glean it from observations, and the biggest opportunity there is that if the current idea of where the fluctuations came from is correct, then there must be gravitational waves of a certain strength, which we do not know, which the uncertainty is parameterized by R, that must exist. It's basic physics, it's quantum field theory in curved space-time, no field theories. No one will argue with the fact that if the matter fluctuations are generated by inflation, then there has to be a gravitational wave background. Okay? So, it's imperative that we go for it. And then how do we go for it? So, then I think Arun probably will show how LIGO works, and it's the same idea. I mean, if you want to detect gravitational waves, you need something where light travel is disturbed. Path lengths are disturbed. Here that is what is happening. You have this plasma screen, and if there is a cosmological scale gravitational wave, then this would be distorted. The plasma screen will be distorted, and that will create a particular pattern of polarization, linear polarization in the cosmic background, which we can measure. With the current technology, we can measure if that current technology can be put on a satellite. Okay. So, this is something that is an amazing opportunity. So, just to put it in terms of curves, I mean again for people who know, these are the parts of the power spectra that we have very confidently measured. This is, you know, the cyan band, okay, with Planck say. Okay. We just need to cover this, and then we have exhausted the information, cosmological information that is there in the cosmological background. I think it is imperative for humankind to do that, I mean in the coming decades. Okay. So, if we proposed a mission, and I mean not we, I mean anywhere in the world you ask them, this is the comprehensive mission you need, which would have this kind of sensitivity, and what it can promise to do is, you know, address a lot of high goals, legacy, you know, cosmology models would improve another, and actually it is like not 10 million, but 1 billion unexpected discoveries. But the main point is it could give you a hint as to where did how did the universe originate, and that is a big deal. I think it is the biggest deal that humanity can think of. So, this is the proposal we had of a modest size satellite, 4 meters, 4.4 meters diameter, which fits into GSLV-3, and we asked ISRO whether they would consider launching it to the second Lagrange point. And you know, many of the people involved here, you can see some of the names here, and at that time they were not in India. So, you know, those arrows point to where I was hoping they will go, and most of them have made it there. This is one of the things that I think also the entire scientific community should look forward to, because scientific and technology community, because it has path breaking science, but it has also very high value science, and it has a huge legacy data. And on the other side, these are the kind of things it will do for the Indian science and technology, right. And this was kind of a sketch of the satellite. I won't get into it, we had all the details. There is a lot of interesting thermal design that is important, like, you know, we have friends from ISC, you can talk to your mechanical engineering department, they might be very excited about the challenges here. And so that is required. There are detectors which have to be kept at 0.1 Kelvin, 100 millikelvin, when the back plane is actually facing the sun and is at 300 Kelvin. So, that is the separation, and this is the refrigeration, 3 cycles of that, but this has been done before. Planck had something very similar. So, it is not a completely new beast, but you know, all these have to be, can be improved further, and we could work on. These detectors are interesting. So, your phone, mobile phone actually detects picowatts of power. I mean, I was very surprised to know that it is that good. Here each detector can detect attowatt of power, and you have to line up some 7,000 detectors, 2,400 or 8,000 polarized detectors to do that, and it is again not something far. This is happening in Antarctica. So, and this is of course in Chile, but Simons Observatory is tiling up these detectors in huge numbers and looking up at the sky, but they have constraints of doing it from the ground, which we won't if we manage to go for a launch. And this is my hope that someday we will be a big partner, even if we don't launch it, we do a major part of it, or we launch it and do a major part of it, to take, you know, cosmology to the next milestone, where we have answered that part of the question of where did the and how did the universe originate. Thank you.
Yes.
There's some question.
There's a question. You can, there's also a microphone, I think. Yes. Is there a...
Yeah.
Yeah.
Any question here? Okay.
Is there-
what is-
So maybe we can take this one.
Oh, no, he's there, he's ready. Okay, sorry. Yeah, please. Yeah, please go ahead.
So what is the current status of this CMB Bharat project? At what stage it is right
Okay,
now?
so this proposal was submitted in 2018, and all I can say is it's still under discussions in ISRO. It's a major do, and also I feel what we have been very clear is this is not something that ISRO can or should even think of doing alone. So it should be with collaboration with NASA and ESA or both, and these are the kind of discussions going on globally. Okay, the reason we have waited is one is the COVID thing, the other thing is still is a plan that Japan will launch a satellite, Lightbird, and this will be kind of complemented by on the ground measurements by the US, where they had a major program called CMB Stage 4. So Lightbird plus CMB Stage 4 could conceivably do some of the science here. Okay, then of course the community has differences about what can be done, not can be done. Okay, it's just around the time when people have started realizing that that also may be not happening, or even if it happens, that's like as far in time as launching a full-blown comprehensive satellite. So this is the discussion that is happening as we speak. I mean, in the last few months. So maybe sometime next year, April, the picture will be much clearer. But I wanted to just take this opportunity to tell every scientific institution that this is a great opportunity for Indian science to get on board with something absolutely path-breaking that could happen in the next decade or decade and a half. On all fronts, it has the same thing, like I could give a whole slew of what areas where people can contribute to this.
Thank you. Yeah. So in terms of precision of polarization measurements, how would CMB Bharat compare to Lightbird?
Compared to?
Lightbird?
Okay, so Lightbird, the difference is in the aperture of the telescope. So Lightbird has a 30 centimeter dish, primary. The problem there is with such a thing is that they can't measure small scale fluctuations. Okay, now the thing is, even if you have the sensitivity to measure the polarization has a contamination from weak lensing, which causes the E modes to become B modes. It's depending on what levels you are trying to get at, that becomes a problem, and it's better to have a single experiment measuring both the large scales and the small scales. The Lightbird plus CMBS4 plan was that data will be used to correct the data in Lightbird. Okay, that probably is going to be difficult. Lightbird would also did not have as much frequency coverage to be very confident about the foreground removal.
Also, Lightbird will not have the small scale measurements?
Small scale fluctuations. So that they the community thought that would be filled in by the ground missions, because they don't need to look at the full sky for the small scales. But okay, this is my own perspective, because I have been in the game before, say, WMAP came up. So at that time there was something like the last stand before WMAP, where multiple experiment results were put together to see what is the cosmology that's emerging. I have myself played that game. I know that you can get anything you want, because there's always a calibration uncertainty that you can play between the experiments and shift shift to the model you want, right? So I don't think a B mode detection which the world will agree to will come from something where two inhomogeneous data sets are being patched. It's very unlikely. That's a very personal view.
Just want to clarify one thing. So, so CMB Bharat would have both small scale and large scale measurements?
Yeah. Yeah, we have a 1 point, I didn't probably, we proposed a 1.5 meter telescope, or 1 meter telescope, 1.2 meter telescope.
Are there any other last questions? All right, if not, let's thank Tarun and we can invite them.
Okay. So thank you, Sushmita, for the work. So our next speaker is Professor Tirthankar Raichaudhuri. So Raichaudhuri did his PhD from IUCAA in Pune, and then he was a postdoc first at CISA in Trieste, Italy, and then he was a postdoc at Institute for Astronomy in University of Cambridge, UK. Then he first became a faculty at Harishchandra Research Institute in Allahabad for 4 years, before moving on to National Center for Radio Astrophysics, Tata Institute of Fundamental Research in Pune, where he is now a full professor. Professor Raichaudhuri works on various topics, deionization, why is the universe ionized now, intergalactic medium, what does the universe look like between galaxies, dark matter and dark energy and things like that. And he'll be talking to us about how the universe's first light emerged. Thank you.
Thank you. So, yeah, I guess you are hearing the third talk from someone who has done PhD from IUCAA. I promise that's the last one in this series. So I'm going to talk about something which kind of follows from the previous two talks. So we will come to a universe which is slightly older than what we have heard so far. And I'm going to talk about the universe which transitions from darkness to light. So let's see what I mean by that. So the very early universe, the kind of things you have heard about so far, particularly the CMB, you are talking about a universe which is extremely smooth. I mean, the fluctuations are very small, and there are no galaxies or stars at those epochs. So the early universe was completely dark. It was just filled up with mostly hydrogen and a bit of helium gas. Clearly, at some point, the sources of light emerged. So the idea is to learn when did they emerge, and my talk will be about telling you how we are planning to use a kind of €2 billion project called the SK, where India is part of, to understand this process. So just to set up again the context using the timeline of the universe. So if you think about the age of the universe, or in terms of size, where size is kind of calibrated in a way that it is 1 today. So the CMB which you have heard about talks about the state of the universe when it was something like 40,000 years old. Its size was like 1,000th of what it is today. Today the universe is kind of 10 billion years old. Now we have learnt a lot about cosmology from CMB observations. We observe CMB using all these detectors you heard about. We also observe this nearby universe using the large scale structure, the cosmic web, as Sriram showed to you. And using these observations, these galaxy surveys, we are pushing the limit to the state of the universe when it was somewhere around 1 billion years old. So now you see, we know the universe, how it looked like from 1 billion years old to current state, about 10 billion years old. We knew how the universe was when it was 40,000 years old, but we don't have direct observational signatures from the epoch in between. This is also the era when the first stars are expected to have been formed. Now this is something we don't know because we haven't observed these epochs. On the other hand, from the theoretical perspective also, there are a lot of questions which are unanswered. So this is a field which is often called final frontier of observational cosmology. In the sense we would really like to go and observe this epoch, and parallelly we would like to work our theories through, make models, make simulations, and understand what may have happened during this epoch. So this is essentially the big paradigm, that the universe went from darkness to this light, and we would like to understand it using theory and observations. My talk will be talking about how we are trying to tackle this observationally. And the first approach would be to go and try to detect these first galaxies directly. And here a recent satellite called the James Webb Space Telescope is like making breakthroughs. It's happening like almost every day. I mean, you get new results from this telescope. What has been shown here in this plot is points which represent galaxies. So from this curve, from this plot, you can read off the intrinsic brightness of the galaxy in this axis versus, for example, the age of the universe. You can look at the top axis if you want. Before JWST, we only had these blue points, which essentially came from HST and follow-up observations. So at that point, we were looking at galaxies from the universe when it was something like 1 billion years old. Okay. And that's what I said. This is the time. This is the kind of state-of-the-art observations we have. The orange points is the state of the field after JWST came. So now you can see these orange points go to much earlier and earlier times, and now we are observing galaxies from the state of the universe when it's like less than 300 million years old. Not only that, we are also observing galaxies which are less bright, meaning you are also detecting fainter and fainter galaxies. So the whole field has completely changed after JWST, and the hope is that as JWST observes more, as it operates for more and more time, hopefully at some point we will reach a stage where we will kind of try to see what was happening during this so-called cosmic dawn when the first stars formed. But that is just one part of the story, because probably because of the way these telescopes work, they are kind of biased towards detecting the bright galaxies. And they might just be the tip of the iceberg, and they may not tell us the complete story. So it is always good to have some backup options. So you find a way to complement these observations with something else. And there comes a concept of using hydrogen. So this hydrogen is sitting outside the galaxies in the intergalactic medium, and they are all over. They are the most abundant element in the universe. And the question is, can we just use the effect of galaxies on hydrogen to study and learn about these galaxies? Now the idea here is simple, and I will give you one example of that. Imagine a universe where all these hydrogen atoms are sitting. Okay, so this is these hydrogen atoms where I have tried to draw a nucleus surrounded by electron, and probably we are receiving some signal from this hydrogen atom if we are lucky. Now let us say a star forms or a galaxy forms somewhere here. What will happen is the radiation from these galaxies can come out and dissociate the hydrogen atom. So what will happen is the signal we were getting from the hydrogen atom will stop coming. Now if we can make some kind of a movie of the universe where we see the universe at early times and then somewhat later and later and later, what we expect to see is at early times it will be full of hydrogen atoms, and then at later times it will get depleted of hydrogen atoms. Not only that, we can also see that atoms which are closer to galaxies will get depleted first. Atoms which are far away are probably still safe till more and more galaxies form. So this is the picture we have in mind, and this is something we plan to use. Now we are not going to look at the galaxies directly, but we want a signal from hydrogen, and using that we now want to understand when the galaxies form, how did they form, and so on. So it's indirect probe. But the advantage is this process will be dominated by galaxies which are representative. Okay? It may not be dominated by the few bright galaxies. So it becomes a complementary probe to the direct detections we see from the JWST. Now that was a cartoon, but this is something where if you run this idea through a computer simulation with appropriate mathematical equations put in, this is what it will look like. So this shows how the galaxies form. As the universe evolves, the cosmic web or the large scale structure forms, and at some point what will happen is you will see these white regions showing up prominently, and they are the places, these are places where the density is very high and eventually stars will start to form. The right hand panel basically shows the evolution of neutral hydrogen. Red is neutral, black is kind of ionized. what you will see is wherever these galaxies are going to form, probably concentrate on this part, you will see black regions are forming here. So it is getting ionized, and then these ionized regions are growing and kind of percolating all throughout. So the idea is you make some kind of observations which detects this signal, and through that try to understand the properties of these stars. Okay. The signal which we are after is called the 21 centimeters line of hydrogen. So neutral hydrogen basically emits a very faint radio signal in the wavelength of 21 centimeter. It happens because some flipping of quantum spin of the electron with respect to the proton. So essentially this will come only when the hydrogen is neutral. So if you dissociate, kind of kick off this electron, then this goes away. So that is precisely the kind of signature I showed you in the previous slide. So this, as this spin flips, this hydrogen can emit or absorb radiation at a particular wavelength called 21 centimeter, hence the name 21 centimeter line. The corresponding frequency is 1420 megahertz. Now as the universe expands, the wavelength of the light will expand and the frequency will decrease. So the wavelength of the light expands as the as the size of the universe. So whatever was emitted at 21 centimeter, if it was like at a very early time, we won't be observing it at 21 centimeter. Again, redshift is something Sriram talked about, and it will probably shift to maybe meter, or the frequency will shift to much lower frequency. So you need low frequency radio telescopes to detect it. And as a result, and this line hasn't been detected from these early galaxies or the hydrogen around early galaxies, a lot of effort is being kind of spent worldwide to detect. So there is a setup effort where people are trying to detect what we call the global signal, that is the signal average all over the sky. These can be done using relatively kind of smaller telescopes, and there is a wide range of projects which are going on. Remember, this is just a selected list. Okay, there are many other projects which are trying to do these observations. The other option is to detect the fluctuations. All these, you could see these black regions, so what we call bubbles forming, growing, merging, and so on. So for those you need to make arrays of telescopes. Okay, so there are various telescopes worldwide which are again trying to detect this signal. And there are two which are of really interest to India. One is SARAS-3. So this is something which is being led by a group in Raman Research Institutes in Bangalore for doing the global signal. And the one which will become important in this talk is the GMRT. So this is a telescope which is built and maintained by the institute where I worked on, that's NCRA. It's situated 80 kilometers from Pune, and it's an array. So it has some 30 telescopes sitting in some area, and it's trying to detect, I mean, among many other sciences, it's trying to detect the signal from the epoch of first stars. Now these telescopes are trying their best, but it's very unlikely that they will be able to reach the sensitivity to detect the signal. So the future then lies in a telescope which needs to be much bigger, much more ambitious, and hence much more sensitive, and that is where the SK comes into the picture. So the SK Observatory, I mean, they like to advertise themselves as the next generation radio astronomy driven big data facility that's expected to revolutionize our understanding of the universe and laws of fundamental physics. So you can see the ambition really showing up here. It's headquartered in the UK, and the telescopes will come up in South Africa, which will look as dishes. So this will be called SK Mid, and then there will be these low frequency antennas in Western Australia. It will be called SK Low. For the kind of science I have been talking about, this SK Low is going to be more important. Of course, till a few months back, I would have shown this picture and would have told you that these are artist impression because this is being planned, except what is happening is SK is being constructed. Okay, so people are actually building this. So this is the first dish in South Africa, a dipole in Australia, and not only that, using these dipoles in Australia, people have also already started to make images of the sky. So this has come up just few months back. This is just one night of observation. This just, I mean, this is not anything where you can do science with, but this shows that the telescopes are working as they are expected to. If we look at how powerful SK would be, what has been plotted here is sensitivity, so don't worry exactly what it is, versus the frequency, and this curve is basically shown for different existing telescopes and SK. The higher it is, the better or more sensitive the telescope is. So there are 2 points to note. Among the existing telescopes, there is a frequency range where GMRT still is the best experiment. So you have a telescope in India existing now as we speak, where you can do cutting edge science which no other telescope in the world will allow you to do if your science is related to these frequencies. Okay. Of course, once SK comes up, they will kind of overwhelm all the existing facilities and they will be much better. And you can see, I mean, they're like really, I mean, much higher in terms of sensitivity compared to the existing facilities. The timeline, although even a few years back SK looked far into the future, but as you can understand, SK is happening as we speak now, it's being built. So now basically the construction is going on. Very soon what will happen is already these collaborations across, across verifying the system and testing some science will start to happen. The community, that is the scientific community, starts to get involved at this stage. Now this stage will start for this SKLO, the dipoles, in the first half of 2027. So we are looking at 1.5 years from now. And some of these activities will probably start about 6 months from now, the planning of these. This is the phase where SK will give out some preliminary data. It won't be fully ready, but you will be able to do some verification of your science. The science you want to do, are all the components relevant to that working? So you start doing that so that once the telescope is ready, somewhere around 2030, you are kind of, you also know exactly what to expect and what to do, and if something is missing, you can feed back to the engineers and hopefully things will work out. SK is important for India because it's an ambitious project, so it cannot be done by one country or one funding agency. So it's a multinational project involving, currently there are 12 members in the SK, 12 countries, and there are various countries who are like almost ready to join. And as you can see, India is part of that. Australia and South Africa are where the telescopes will be built. UK is where the headquarters are. There are various countries in Europe. This is Canada and so on, and you can just read off from the map if your favorite country is there or not. SK, although I motivated the whole thing from the cosmological perspective, remember it's an observatory. So it is not going to do only cosmology, but a wide variety of science. I'm not going through this slide, but this is just to show the range of science it's expected to do, hence that ambitious statement at the beginning. Okay. I want to spend some time on like the history of Indian involvement in the SK. So in the 1990s, the radio astronomy pioneer in India, Govind Swarup, was one of the person who gave this idea about making a huge telescope, probably involving multiple countries. It evolved to and it started to take shape, and India got involved in so-called in the so-called design phase of the of the SK, and it was leading the development of what was called the Telescope Manager software. In 2015, India officially joined the SK organization, as it was called at that day. And those days, and then what happens is this SK from ordinary organization, it transformed into something called an intergovernmental body. So which means now the governments would have to sign a treaty to join the SK, and that's what India did. So it became something which is which has more permanency in some sense. So this is what happened in 2024, where government allowed us to have the funding and gave the approval for joining the SK Observatory. Now we are kind of what we call full member of the SK. Remember, parallelly our own GMRT, the upgraded version of it, plays an important role in testing ideas and technologies for the SK, and it is designated as one of the SK pathfinders. There is a lot we are contributing in terms of industry, and I probably won't have time to go through these in full detail. Okay, I know what happened. Okay, we are contributing to software as well as hardware, and we also have a plan to host something which we loosely call a data center, but in SK they will be called the SK Resource Center. So they will be hosting data and computational facilities which can be used for accessing and analyzing SK data. Of course, in terms of science, I mean, as if somebody attended this meeting would have already known that in many science areas, particularly related to cosmology, Indian scientists are really leading and participating in a big way in these key science projects. But then there are other areas beyond cosmology also where Indian scientists are playing a leading role. So that is something to look forward to. In India, there is something called SK India Consortium which exists. It's a collaboration of 24 institutes already, and from this map you can make out the institutes. But beyond this consortium, there are of course many other scientists who are contributing. We also have science working groups which brings the scientists together, and we keep on holding meetings, workshops, training schools, and I hope at some point we can come to IMSC to host one of these meetings for the SK. So that essentially brings to the end of my presentation. So as I was trying to tell you that the first stars mark a turning point in cosmic history, and one is trying to detect their signatures through neutral hydrogen, and SK is going to kind of play a very important role to do this, and India is a major partner who is contributing to science and technology, and that essentially will help us access the resources directly when the SK is built. So there is a lot to look forward to. Thank you very much.
Thank you, Professor Raichaudhuri, for talking about the first light in the universe. Are there questions?
Thank you very much for the wonderful talk. So my background is not in physics, unfortunately, so I'll just ask a very lame question, which is what decides the location of these facilities, these observatories like South Africa, Australia,
Yes.
Pune, and so on?
Yeah, no, it's a very interesting question. So radio astronomy, and particularly the kind of science we want to do, one of the major challenges is man-made interference. So our mobile phones, our electronic appliances, all these electric lines. So you need to go to a place which is kind of far away from civilization. In fact, when GMRT was built, it was built in a relatively remote location. Unfortunately, that remoteness is not true anymore. So essentially, when the site selection happened, it was very clear that firstly, southern hemisphere is kind of better suited, probably because, yeah, this population density is less. And both these places, both South Africa and Australia, the places where these are being built are deserts. So there is virtually no people there. So most of the electronics it's there will be probably because of these telescopes themselves, but we know how to handle them. So these essentially helps us choose the sites for radio telescopes. So, yeah.
So, hi, so will you cosmologists, because I know presently there is no plan to store the raw data, but if raw data is stored, will it help you cosmologists anyway?
Yes. Short answer is yes, but we
So-
also don't know how. So, okay, just for others. So, the SK data rate will be so huge that it will be almost impossible to store the raw data as it comes out of telescope, which is typically done for the telescopes today. So, the plan is that SK will kind of process the data to some extent like live and will give you these processed data. Now it will work for many of the science areas, but there are some science cases where getting the raw data is essential, because you are really doing something which is cutting edge, and this processing will probably lead to loss of information.
Yeah, in future when technology and algorithm improves, so is it possible to do something, means to speak to and convince SKO to store the raw data, please?
Very unlikely that SK will have the ability to do that. My understanding is, in that case, the individual projects will have to at least contribute to some extent to, find a way. It has to be mutual, of course. But if you just rely completely on SK without trying to contribute something from the user side, it may not be possible.
So you mean that particular working group provides storage facility or something?
To some extent, yes. They have to do something. Yeah, or some resources where.
So, but if it is a subgroup of subgroup, so.
I don't think details at that level has been worked out.
Okay.
But this is something I know the cosmology group is trying to, or the Epoch of Reionization group is trying to negotiate with the SK. But it's very difficult to tell you what the status is.
Okay, there's another question.
So this is just a follow-up to what she was saying. So what kind of raw data do you need? Do you need really the raw data, or would it be some type, would a compression work, which then can be sort of, expanded with some loss? Would that kind of data work, or do you need the absolute?
No, yes, compression with some loss may be okay, but the way SK is trying to do is kind of smoothing the data, essentially, in time, probably. And that may not work. Okay, or time or frequency or whatever. So, yeah, so it is not just, it's not a question of compressing. So these are probably anyway coming in like binary digits, and beyond that, it's not very,
Yeah, because just storing would be enormous, and a lot of this data has a lot of noise in it, and it's like and I see that there's a big data analysis component thrown in with these observatories, which makes sense.
Yes.
So it was just like follow-up that maybe some type of compression engine which does not store losslessly. So like if you expand it back, there will be loss, but maybe that's measurable and detectable, so that you can interpolate back.
Yeah, I understand. So there's no doubt we have to think along those lines. So we really cannot store the raw data. So some compression needs to be made. But that is something which the users of that science will
how
have
much
to
they
do.
can tolerate, right? How much loss they can tolerate.
Yes, so those studies are being done, and that will depend from science group to science group and so on.
Thank you.
Yes. And even in this case, they may not be planning to store the data for entirety, but they need some time to analyze it at least.
Okay, are there?
One small thing, she is our colleague in theoretical computer science, so I think people
I
like her
realized
can-
that from the second question.
Yeah,
and
so I think people like her can help in this.
So even within the Indian context, we are really looking for help from the computer scientists. Currently we are doing it through SK India Consortium. So whichever institutes have like computer science departments, and if they are interested, we are really reaching out to them to help us. To whatever extent they can. Of course, these are done really in the Indian context from our side, but these are done by all other countries, including the SK Observatory, in their own way. So this will become inevitable in probably in the next few months. We have to start thinking about these things. So I'm happy that people are talking about this.
Yeah, there are no other questions? Is there? Upstairs? Yeah, I didn't see anybody. Okay. Yeah. So if there are no other questions, let's first thank Professor Raichaudhuri again for the wonderful talk. And for the last talk, I hand it over to Professor Adhikari.
All right. Our next speaker, we're really delighted to have Professor K.G. Arun. He is a professor of physics at the Chennai Mathematical Institute. Professor Arun started his career doing his bachelor's in Cochin University, after which he did following which he did his PhD in the Raman Research Institute in Bangalore. He was then a postdoctoral fellow in the Institute of Astrophysics in Paris, and following which he was at Washington University in St. Louis, and following that he came back and he was here as a professor in CMI. Professor Arun is interested primarily in these exotic compact objects like black holes, neutron stars, and is particularly interested in looking at tests of general relativity from these compact, dense objects. And he's going to be telling us about what we can learn about these end stages of life, of stellar life from instruments like LIGO India. So over to you, Professor Arun.
Yeah, thank you so much. So I would like to thank the organizers for the invitation to speak on this outreach event. It's always great to be here in IMSC. So as the previous speakers have given you the kind of background, so I'm going to talk about the late universe and not so much about the early universe, using a new way to probe it that's called gravitational waves, and that's what I'm mostly going to talk about. So this is a picture that, this is another variant of the picture that you have seen, starting from the Big Bang. We are where we are here now, and we want to understand the nearby universe, nearby in the cosmological sense, and how we can probe it is what I want to address. So we should start, I am going to give you a crash course on universe today, whatever that means. So we know that we are a member of the solar system. We are one of the planets that go around the sun. And sun, as we know, is a star, and the solar system is a gravitationally bound system where things go around the sun. And sun is a star, but it's not a very special star. This is one of the several stars in our universe. And as Sriram had mentioned, we are all members of the galaxy. It's called Milky Way, which already contains a huge number of stars. And if you go out in the structure, as again Sriram mentioned, that there are galaxy clusters. These are galaxies bound gravitationally, and this is probably the largest gravitationally bound system that we have got, and everything that we see should be happening in this kind of thing. So it could be, so we start with the solar system, galaxy clusters, and that's where that's how the structure is distributed. So now the question is, how do we know and how do we probe these objects? So there are various ways to probe them. You can call them messengers, cosmic messengers, and mostly we know them through light in various bands, as was kind of talked about. We also see cosmic ray particles and neutrinos and so on. We get some idea about relatively nearby universe. And what I'm going to talk about is gravitational waves is a new way to probe the universe, and that's what I'm going to talk about. But it's good to start with what we know. So this is an electromagnetic spectrum where we, from the low frequency radio all the way up to high frequency gamma rays, and we do use instruments or things that we use are happen in this band. So astrophysically what we do is that any astrophysical process that produces light in this band is what we are probing. And to kind of do that probe, what we do is that we launch telescope. Either it can be in the it can be on the ground or it can be in the space, and this will tell you the various types of instruments that is required, that is specified to the particular frequency band of the electromagnetic spectrum that you want to observe. And you observe, and this is how far you can observe will depend upon your sensitivity, but you observe in various bands using all these telescope, and then you learn whatever we know currently about the universe is coming from these telescopes which have been there, most of what we know. Now I have to also give you a crash course on the life and death of stars, because that is what I'll be talking about. And how, kind of first question is, how heavy are stars? And there are the stars mass can range from very, like 0.5 all the way up to 150 and even more maybe. And most of the, there are stars of different type, more smaller massive stars are more abundant. And stars also happen in binary, so I think it 80% of the stars that we know in our galaxy are in binary systems, and it should be true elsewhere too. So these are stars which go around each other. If you have taken a look into in a clear night sky, you would have seen two stars very close to each other. So these are like binary stars, and they play a very important role in what I'm going to talk about. So these are stars which go around each other, whose light we see, and they would be, as they evolve, they become very important for what I want to talk about. So this is about stars, how they are, and it is important to understand how they die, because they are burning hydrogen, helium and so on. At some stage when they exhaust the fuel that they are burning, they are going to, if they are massive enough, they are going to explode. So the inner core is going to implode and the outer envelope is going to explode, and whatever is on the outer layer is going to explode. This is called a supernova explosion, and we have seen many, a few with naked eyes also, but within various bands we observe them quite routinely. And this is typically how the end of a massive star would result in some kind of a supernova explosion. Now, what happens after supernova explosion depends upon the mass. So what is left behind after supernova explosion, it can be a white dwarf, which I will not be talking about at all. And if the mass of the star is 30 times, slightly less than 30 times the mass of sun, and between 10 to 30 times, you may end up with a neutron star. I will come in the next slide about that. If it is even more massive, which is where the gravitational field or the gravitational mass is so strong, it will lead to what is called a black hole. And the last two entities, the neutron star and the black hole, is going to play an important thing in what I'm going to talk about. So let's ask what is a neutron star, and people like Manjari are experts here, and this is a one slide summary of extremely concise summary. So as the name indicates, this is a star composed of neutrons mostly, and it is like, it weighs like sun but compressed to 10 to 15 kilometers. That means it's extremely dense object and very compact and very dense, and if you were to take a spoon of a neutron star, it could weigh as much as Mount Everest. Okay, so this could be emitting in radio and sometimes in X-ray and so on. That's all electromagnetic waves. So this is one of the end products of star, depending upon the mass of the star. Now, what if the mass of the star that exploded was even more? If it's very heavy, it will, even, so in this case, the gravity is balanced by neutron degeneracy pressure, the fact that because of the fermionic thing, two fermions cannot be in the same quantum state, that acts as against the gravitational attraction. But if the mass is even more, the entire star is going to collapse. Outer layer will explode, but the inner core is going to collapse to a single point. You can call it a singularity or whatever. But then this is an object from which nothing can come out. Light cannot come out, because it's such a, typically it's got, everything is condensed to a single point, and you can think of a horizon around it. But of course, things can fall in, and gas can fall in, particles can fall in, and that way you can still get some electromagnetic signature, hopefully of things which are which is falling into a black hole. So now the important question is that, typically I told you that massive stars will end up as a neutron star or a black hole, and if you have a binary star system that I started off with, right, so they will also die, and you can have multiple outcomes. So one can be, you may end up with a star system which has got two black holes. It's called a binary black hole system. You can have a system which consists of two neutron stars. I will call it a binary neutron star system. And you can also have a mixed system. One may be a black hole, one may be a neutron star. You can call it a black hole neutron star system. So these are like the end products of a binary evolution. Depending upon, there are many complex physics that goes on, but typically they may end up as binary black holes or binary neutron stars, and they are going to be the topic of what I want to talk about. So at this point, I want to ask a question that can we, beyond light, not just using light, are there other ways to probe our universe? And the answer is yes. That is what is called gravitational waves. So just like electromagnetic waves, which are emission, you have an accelerated charge that gives you electromagnetic waves. If you have accelerating masses, you can get what is called a gravitational wave. So in the first talk, I think Sriram showed you this, if you have space-time and you if your gravity, if you're gravitating matter in the space-time, it is going to curve the space-time. And if this object, so I'm showing you the curvature for these things, exactly the same plot that Sriram was showing. And now if these objects are dynamical, suppose one star is going around each other, one black hole is going around each other, or they are accelerating in some way, it is going to send out ripples in the space-time, because things are, the space-time is getting disturbed because of the dynamical motion of these objects, and that sends out these ripples in the space-time curvature. This is, naively speaking, what is a gravitational wave. And this is important because now if you are able to observe a binary black hole merger far away or a binary neutron star merger far away, we can use the waves that are emitted by them to probe that region of the space or the phenomenon in more detail. So that way you don't have to rely on light anymore. You can use gravitational waves to probe the dark, meaning which doesn't emit any light. You can still probe because gravitational field is there, and time varying gravitational field is gravitational wave, and if you can detect them, you can probe you can probe the universe and at various distances using gravitational waves. Now I want to show you one animation which is about how the binary black hole merger happens. So what I'm going to show you is an animation from a real numerical simulation. You are solving Einstein's equation on a numerical grid, and this is two black holes which will be, so you start with two stars orbiting around each other, which will end up as two black holes orbiting around each other, and according to Einstein's theory, this will emit gravitational waves, and as the waves will carry energy which has to come from the orbital energy, the orbit will shrink. When the orbit shrinks, the two black holes are closer, therefore gravitational field is stronger, and therefore emission is even stronger. So this is like a runaway process which will bring them close to each other, and eventually they will merge to form a single black hole. And this, so this is the process. You bring two black holes from far away, and because of the emission of gravitational waves, they merge. And what I'm going to showing you is like an animation of that with this wave. So they're waveform. So when they are initially far away, you will get a almost sinusoidal kind of wave. But as they come closer, which is where the most intense emission happen, you have an increasing amplitude and increasing frequency. That will lead to this is when the new black hole is formed, and immediately they kind of dance out and then there is nothing. So this is the animation. These two black holes are going. So this this red color is showing you the strength of the gravitational field in some sense. So they are kind of far away, and you can see that emission is almost sinusoid. And until they come very close, so they are. You can see the orbit is shrinking because these orbits are kind of what's called inspiraling, because they come they spiral in. And now towards the last few cycles, you can they go faster, and they emit stronger kind of thing, and because they are tighter orbits, the kind of frequency of emission is also high. They kind of increase until so you can see that now they come very close, and at these peaks when they think they have now got a black hole, which kind of immediately kind of settles down. So this is the this is same this picture will apply to binary neutron star mergers also, where you have two neutron stars orbiting, they come closer and they eventually merge, and the gravitational waveform that I showed you would be broadly the same, but the details will depend upon the spin of the black hole, mass of the black hole, mass of the neutron star, etc. So that is what we use to infer these parameters. Now, how do we detect them? Because this is a very, typically the kind of imprint this will be, these passing gravitational waves will make on Earth is going to be 1 by 1000 of a Fermi, or less. And so you need very kind of sensitive instrument to detect these waves, which was being built over the last few decades. And now we have a few operational detectors. It's called LIGO, 2 LIGO detectors in the US. You've got Virgo, which is in the Europe. You've got a Japanese detector called Kagra. And then, I'll also come towards the end that there's a plant detector in India called LIGO India. But, so these are the Virgo and Kagra are the detectors which are operating. So you can see this picture of, I'm not showing you how LIGO detect, but these are very, this is 4 kilometer by 4 kilometer arm length interferometers, which are sensitive and can measure this, the kind of displacement of two particles by, which is by 1 by 1000 of a Fermi. Kind of instrument which was built over time, and they were being commissioned in 2015, during which our first detection of gravitational waves happened almost like a decade ago, which is on 14th September 2015. So we call it GW 150914, year, month, and date. And this was a binary black hole merger about 1.3 billion years ago. And the signal, this is a Nobel Prize release, which says that the signal was weak, and we needed instruments such as LIGO to detect this kind of minute changes that are made due to the passing gravitational wave. So these three gentlemen, I think Tarun also mentioned that Rainer Weiss, Barry Barish, and Kip Thorne were awarded the Nobel Prize for contributing to various aspects of these efforts over the last few decades. And that way, it's a kind of very important thing that happened. So just to, if you want to understand what happened exactly, so this is again, I'm showing you the picture. You have got two black holes kind of inspiring in, and you have initial almost sinusoidal thing, but as they come closer, you can see an increase in amplitude and shrink, the kind of increase in frequency. And what is shown here is typical speed of that black hole. So when they merge, they're like hitting each other with the speed of like half the speed of light. Is that kind of relativistic thing. So it's a very strong field and relativistic event that we witness when this kind of thing happened. And at least this event is due to the merger of two black holes, one which weighs 35 times the mass of Sun, another which is 30 times the mass of Sun, and it happened at around 450 megaparsec, which is in the astrophysical scale. And that merger led to a new black hole, which is the 65 is the sum, and 3 m Sun c square was the energy that was radiated out in the form of gravitational waves. So this was the kind of first event, and we did have a couple of events after that in 2016 itself. But another big thing happened here, where we discovered a binary neutron star merger. Now, as black holes cannot emit light and so on, we don't expect any light from binary black hole mergers unless they happen in some places. But this is first event where we observed both light and gravitational waves from the same source. So we found a gamma ray burst, which is believed to be originated due to this merger of two neutron stars. And we found that after the merger happened, 2 seconds roughly after that, we found this event called GW 170817. It is the first time that we are observing two messengers kind of simultaneously or independently. So that way you can say it's like a multi-messenger astronomy. We use light and gravitational waves to probe the same kind of system. And since then, we had LIGO and Virgo had several observing runs, O1, O2, O3, O4. We are now taking data in O4C, that is where we are. And we have detected like several, 290 sources in total, most of which are binary black holes, and a handful of them are binary neutron star black holes. So we have been observing them over the last few years, and that way we have been able to do kind of several things. We could take a census of black holes and neutron stars in binaries. We could ask the question whether the waveform is as predicted by GR, that is strong field test of GR, or asking was Einstein right, and how rapidly is the universe expanding. I couldn't get to that, and composition of neutron stars, and so on and so forth. So this is what we do. We use these instruments or these sources and gravitational waves to do these things. Now in the last 5 minutes, I want to talk about LIGO India project. I mentioned that these are the kind of existing kind of operational detectors, and LIGO India is here, which is far away from the US. So once LIGO India is constructed, the engineering drawing tells this is how it is going to be. This the 4-kilometer arm thing. It's a joint effort led by IUCAA, RRCat, IPR, and DSEM, which are the institutes that are leading, which have got different they have got different tasks to manage. And so once we have LIGO India, why do we need LIGO India? Once you have LIGO India, you expect that the localization of the source, which is very poor now, can improve. That is, we can very sharply localize the source in the sky, as well as enhance the sky coverage. That means you can see sources from a larger portion of the sky. It will also increase the duty cycle of the network, because when some detectors are not operational, you still have more detectors. That way it will increase the number of sources, because it will increase the duty cycle. And you can carry out, because there are multiple detectors independently observing them, you can carry out new tests of GR. And there is, interestingly, you can also have very interesting synergy with other electromagnetic telescope where you observe, like the 17817, where we expect light and gravitational waves together. So it's a very important player at a very important time. And so this is showing you this is the localization to 620 square degrees was the original one. If LIGO India was operational, you would have got around 10 or 5 square degrees. That's where this should be. So by having a wide baseline improves the sky coverage significantly. I'm similarly showing you that the 17017, the binary neutron star merger, could have improved, the source localization could have been 3 times better, which would mean that you can follow up the light source much faster, and maybe you can detect some early emission which are associated with that. So it's very important to have a large sky localization, which LIGO India will bring in. And of course, LIGO India will interface with various aspects of thing. For example, starting from kind of theoretical stuff, fundamental physics here, to more of a technology-driven thing. Various technologies which are required have to be developed here, and we will, we'll have to do that. And on the computing side here, and on the education thing here, and on the other hand, that you are going to have interface with all other electromagnetic telescopes in India, which kind of ranges from this. LIGO India is going to make an impact on all these fields, and therefore it's a very important national project. LIGO India community is spread out over India. I'm just showing you the kind of thing. There are around 16, 17 institutes which contribute, and there are 2 in Chennai, both IIT Madras and CMI. And this is still growing because we are still getting thing to improve the number of the people who want to join and kind of contribute and so on. And it is important to notice that significant contributions from the Indian community has gone into all the discoveries, both the first discovery as well as the subsequent ones. So it's, again, it's important to say that these days astronomy is astronomy without boundaries. So you need to interface. There is a lot of healthy overlap that LISC has got with INPTA, which is a pulsar timing array. I could not talk about that at all. SKA, I think Tirth already talked about, and TMT, 30-meter telescope, which is another kind of another big project to which India is investing in. So there is a very healthy synergy, both in terms of science and in terms of management. I mean, there is a lot of things to learn either way, and we are in the process of kind of interacting with people. So in future, we expect that LIGO type detectors will improve the sensitivity by 10-fold. There are new kind of detectors which will scan 1,000 times more volume of the universe. There is going to be LISA as a space-based mission which will observe the universe in millihertz gravitational waves. And you also have pulsar timing arrays which are using pulsar timing as a way to probe gravitational waves in nanohertz. And so you would expect that next decade is going to be a decade of multi-band gravitational wave astronomy, and LIGO India will play an important role in terms of doing these synergies. Okay, this is my last slide. I want to tell that we start with a very, LIGO started with a very nearby sources, but as you go out, you can, you can be probing very early, late universe as well, not so early as you think. With that, I'll stop and I'll take any questions here. Thank you so much.
Hi, so just wanted to ask, if you do not have the light detection after the gravity wave detection, how do you distinguish between very light black hole binary and a heavy neutron star binary? Is there a distinction?
No, so I think there is a distinction you can make. For example, if it is a neutron star, the gravitational waveform will have imprint of the structure of the neutron star, the equational state, for example. But it is true that when the black holes are light and signals are not so strong, our ability to distinguish a light black hole from a heavy neutron star becomes less. And this is a problem, but that's, but in principle we can do, but it depends upon signal to noise ratio, that whether we can do that or not, even in the absence of light.
I see. Thanks.
No, so there is no update, meaning we are analyzing the O4 data, and we will be having a paper in the next couple of months or something. So I mean, they'll be improving upper limits, but I do not know how, I mean, I am not an expert to say how interesting the upper limits will be. And continuous waves, you know, it takes a lot of time to analyze because they're computationally heavy thing also. So that's all what I know. I'm not being closely following the thing. Yeah, correct, yeah. So I think I'm saying the data is being, so there are different types of analysis that is going on. And because there are also searches for dark matter and so on, right? So there are various things. Some of them will conclude in smaller time and can set some upper limits on this kind of quantities. And there can, some of them will be like a targeted sources which may take more time to run and so on. So I do not know the time scales, but I'm expecting the next few months the offer analysis should be complete on most of these things. No, so there are two things. So DESIGO is a Japanese mission which is a too ambitious a mission. I don't think they have got any funds so far. They are still trying to do something of that scale. What on the, there is a Chinese proposal which would, you know, which is under consideration. You would never know them until they fly. So I don't know about that. But in the Indian context, there is an activity going on to see, with ISRO we are talking to see if there is an interest and so on. But they are in the early stages, so we have expressed interest, they also expressed interest, but unless we do a detailed science study, feasibility thing and so on, I mean, it's too early to say. But there is interest, and we are trying to pitch for a decihertz thing in India also.
Any last questions? So maybe I can ask if there are any last questions for any of our speakers. All right, so I'll let you. Oh, good.
Which was a much heralded collaboration between ISRO and NASA, yes. Do you think that augurs well for the type of thing, multi-collaborative space observatory you were proposing?
Quite perceptive. Yeah, I was replying to emails from JPL today morning. Yeah, so there has been a strong interest from